Okay, so let's get started, please. Can somebody tell me? Does anybody remember what we were doing? Let me write something on the board. If you can tell me what this means, then you remember what we're doing.
The sum of a's from n equals 1 to nk. Or to infinity.
That's what it says. Yeah, it says the sum of the an from n equals 1 to infinity is or equals l. Right? That's what this says in English, right? If you read it, it says the sum of the a sub n from n equals 1 to infinity equals l. Okay, but we said last time that we're not going to be talking about it. So that's not exactly what we mean by this. We don't really mean that we're taking 1 plus, and then we're adding up somehow all of them and getting L, right? We give a meaning to this, right? Well, does anybody remember what this meant to us? Very clear. This had a meaning, Hunter, yeah.
I remember the last thing we said is it creates a consistent way of dealing with sums.
Mm-hmm. Right, so this is, so we made up a way that will allow us to deal with this idea without running into craziness, like, one being equal to 2 or something like that. Anybody remember?
Partial sums?
The sequence of partial sums, yeah. So what this meant to us, this was a shorthand, right? This was just a shorthand, right? Was a shorthand was an abbreviation for a particular statement that was an abbreviation for the sequence of partial sums right, where the sequence of partial sums Sn, where S of n was, the sum from a sub k from 1 to n, converge to L. Right? That's what this meant, right? That the sequence of partial sums converges to L. Okay. Right, and we did this example of the geometric series. Right? Our example was the geometric series summation, r to the k from k equals 1 to infinity. From k equals 0 to infinity turned out to be 1 over 1 minus r, as long as the magnitude of r was less than 1. Okay. Right, so if I say the summation, summation, 3 halves to the k, from k equals 0 to infinity, equals, 1 over 1 minus, 2/3. What am I doing? Was 1 minus 2/3, in other words, 3. Right? If I say this, I don't mean actually that you somehow add up all these powers of 2/3 simultaneously, but rather that you look at the sequence of partial sums and you see what that tends to, right? You look at 1 plus 2/3, 1 plus 2/3 plus 2/3 squared, 1 plus 2/3 plus 2/3 squared plus 2/3 cubed, etc., and you look at that sequence, and that's what this means is that what this statement means is that this sequence of partial sums tends to 3. Okay. So don't get confused. Okay. be confused by what this means. This, when we're talking about infinite sums, really what we're talking about is the sequence of partial sums. Okay, so okay. Now, sometimes you'll see this, you see this written out, like, you may see something like this: 1 plus 2/3 plus 2/3 squared plus 2/3 cubed plus blah blah blah, and they'll write some dot like this. That's just an abbreviation for this also. Okay, again, don't think that you're adding up all these things simultaneously. This is just an abbreviation for the sequence of partial sums. Maybe I'm belaboring the point too much. Okay. 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 So let me do another example of an infinite series. Excuse me. So here's another kind of standard example of an infinite series. Another kind of standard example. That you see when you're first reading these infinite series. Okay. Summation 1 over k plus 3. K from 1 to infinity. Okay. So somebody says, what does this converge to? What does this converge to? So you'd have to look at the sequence of partial sums, right? Right. So I mean, if you just started writing things out, you'd say, okay, well, my first term is 1 over 1 times 4. My second term is 1 over 2 times 5. 1 over 3 times 6. 1 over 4 times 7. Blah, blah, blah. So we're looking at this, this infinite sum. Okay, it's not really obvious what this is going to converge to. Okay, but there's a trick. 1 over k plus 3, you can write using partial fraction decomposition. Okay, so you take the partial fraction decomposition, right? This is going to be some constant over k plus some constant over k plus 3. Use partial fraction decomposition, and you end up with this. It turns out to be 1/3 of 1 over k minus 1 over k plus 3. Okay, if you work it out. So, you get that A is 1/3, and you get that B is negative 1/3. I'm sure you can do it. It would take you a minute, but let's save that minute for something else. Okay, so let's look at. We need to look at the S of n's, right? The sequence of partial sums. Sequence of partial sums. Okay, so let me write it this way. Sn is going to be a1 plus a2 plus a3 plus plus a sub n. Okay, of course, right? And a1 is going to be 1/3 of 1 over 1 minus 1 over 4. Right? A2 is 1/3 of 1 over 2 minus 1 over 5. Right? A3 is going to be 1/3 of 1 over 3 minus 1 over 6, and so on and so forth, right? Blah, 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 up until 1/3 of 1 over n minus 1 over n plus 3. Maybe I should put in a few more terms. Sorry. I'll put in a few more terms just to show you, so you can see what's going to happen. 1/3, 1/4 minus 1/7, 1/3, 1/5 minus 1/8 plus da 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 da, right? Ends up 1/3, 1 over n minus 1 over n minus plus 3. Okay. Let me write this up a little more plainly. 1/3 of 1 over 1 minus 1 over 4 plus 1 over 2 minus 1 over 5 plus 1 over 3 minus 1 over 6 plus 1 over 4 minus 1 over 7 plus 1 over 5 minus 1 over 8 plus 1 over n minus 1 over n plus 3. Okay, who sees what happens? Elizabeth.
They start canceling each other.
They start canceling each other out, right? The 1/4 and the 1/4 cancel, or the 1/5 and the 1/5 cancel, the 1/6 and the 1/6, which I didn't like, cancel, right? Right? So you get a bunch of cancellation occurs, right? Right, the terms in the middle cancel out, and what you're left with in the end is 1 over 1 plus 1 over 2 plus 1 over 3. Everything in the middle cancels, and then at the end you end up with negative 1 over n plus 1, negative 1 over n plus 2, negative 1 over n plus 3. So what you get is that partial sum is going to be 1/3 of 1 plus a half plus a third minus 1 over n plus 1 minus 1 over n plus 2 minus 1 over n plus 3. Okay, so what happens to the sequence of partial sums? As n goes to infinity, what happens to the s of n's? Well, these things are just going to go to 0, right? These things go to 0, and you're left with 1/3 of 1 plus a half plus a third, which turns out to be 11/18ths. Yeah, Chandler.
What was the point of doing the partial fraction decomposition?
The partial, because if you look at it like this, it's not really clear what's going to happen, right? But if you do the partial fraction decomposition, then you see that a lot of cancellation occurs, right? You see that a lot of collapsing occurs.
Is that partial fraction decomposition, is that like taking the derivative, or is that just finding out what k was? Like, what values will we find using partial fraction?
So we took this thing, right, and it turned out to be 1/3 of 1 over k minus 1 over k plus 3.
Okay.
Okay, so it just partial fraction decomposition that we did before. Yeah, Maddie?
I'm confused still why in the end, like on the bottom row, if we include 1 minus 1 over n plus 1 minus 1 over n plus 2. I don't understand why that's going through.
Okay. Let's look at let's do one concretely, and you'll see what happens.
Okay.
So let's look at let's say like S7. Okay. Okay. S7 is going to be 1/3 of 1 over 1 minus 1 over 4. Right. This is right. That's from the first term. We get 1/2 minus a fifth plus 1/3 minus a sixth. Right, plus 1/4 minus a seventh. Right, that's the first 4 terms. Plus 1/5 minus an eighth. Plus 1/6 minus a ninth. Plus 1/7 minus a tenth. Okay, right, this is the sum of the first 7 terms. Right, and you see what happens. This negative fourth kills off the positive fourth over there. Right, the negative fifth kills off the positive fifth. Negative 6 kills off positive 6, right? Negative 7 kills off positive 7th. Okay, right? So all these terms are gone, right? But that's all the cancellation that occurs, right? That's all the cancellation that occurs. These first 3 guys, 1/2, 1/3, I'm sorry, 1, 1/2, and 1/3, never get killed off, right? Because the negative guys start with 1 over 4. Okay, right? Now on the other side, the 1/8, 1/9, 1/10 never get killed off because the positive guys end with 1/7. Right? The positive guys end with 1/7, so the last 3 guys will survive, right? And the negative guys begin with negative 4th, so the first 3 positive guys survive, the last 3 negative guys will survive. Okay, and that's what happens here.
Okay.
Thank you.
So you could have also just written, like instead of, you could have written 1/3 times 1 over n plus 1 over. Just kidding.
Okay, good. Good. Yeah, sometimes it's hard to see with the abstract form. Write it out concretely and you'll see how it works out.
Thank you.
Yeah, but on the other hand, in order to do math, you have to be able to move to the abstract. And sometimes the concrete stuff will mislead you. Okay. Okay, so this is just another example of what we mean by, so what we get in the end is that this infinite series sums to 11/18, right? This infinite series sums to 11/18. What do we mean by that? We mean that the sequence of partial sums converges to 11/18, right? That the sequence of partial sums, which we figure out is this, converges to 11/18. Okay. Okay. So this is all just to tell you what it means for when we say an infinite series equals some number. It means that the sequence of partial sums converges to that number. some basic theorems about infinite series. Basic theorems about infinite series. So suppose you have an infinite series and it converges to some number. So suppose you have some infinite series and converges to some number. And I take a different series, and that's going to be some constant alpha. So you take the sum of this guy where all the terms are just multiplied by alpha. Then what do you think is going to be the limit of that? If you multiply all the terms, you have one series that converges to L. You multiply all the terms by alpha and you sum it. What do you get?
So alpha L.
Alpha L, right? Right. So then, right, this is going to be alpha L, which makes sense because the sequence of partial sums of the new guy, the sequence of partial sums of this is just going to be the old sequence times alpha, right? It's going to be alpha times the sequence of this guy's, right? The sequence of partial sums of this is alpha alpha times the sequence of partial sums of the original series. Right? So if this sequence of partial sums converge to L, well, this guy's sequence of partial sums is just alpha times it, so it'll converge to alpha L. If you have another sequence, B sub k, that converges to M, then the sum of this is going to be what? Tanima?
Is it just L plus M?
Yes, L plus M. L plus M. Okay. Right? And for the same reason, right? If you have the sequence of partial sums of this guy is going to be the sums of the sequence partial sums of these two guys, right? And so they'll converge to that, to the sum. So this is basically saying that for infinite sums, in some sense they do behave like finite sums, right? So if you have a bunch of numbers, 1 plus 2 plus 3 plus 4 plus 4, well that's 10, right? And if I multiply them all by 5, well I get 5 times 10, right? That's all we're saying here. Right? But what this is saying is that it's still true for the infinite series as it is for a finite sum. Okay. Okay. So right. Let me just say that this theorem is just a restatement of the theorem about sequences. Okay, I feel like I'm not getting this point across. So let me try even harder. Okay, so everybody watch for a minute. Okay, everybody watch for a second. Okay, so what does this mean? This means that the sequence of partial sums, S of n, converges to L. Right? Means its sequence of partial sums. Its sequence of partial sums converges to L. Right? Okay. Now, look at this thing. Alpha A sub k. Okay. This guy's sequence of partial sums, let's call it T sub n, is just alpha S sub n, right? Right, because the sequence of partial sums is A1 through AN. This guy's sequence of partial sums is alpha A1 to alpha AN. Right? Well, that's just alpha S sub n. Right? Right? Okay. And then we have this theorem that says if you have a sequence and you multiply it by alpha, if you have a sequence that converges and you multiply it by something, then it will converge to the limit of the other guy multiplied by alpha. Right? This was the limits in arithmetic statement. Okay? Right? So this guy's sequence of partial sums converges to alpha L by limits in arithmetic. Right? And so this is going to be equal to alpha L. Okay? Same thing about the other guy, right? This guy has, this guy converging to L means that its partial sum sequence converges to L. This guy's sequence converging to L means that this guy's partial sum sequence converges to M. Excuse me, converges to M means that this guy's thing converges to M. But we also have a theorem that says then the sum of these sequences is going to converge to the sum of the limits, right? And that tells us that this thing converges to the sum of limits. Okay, so all this is just limits in arithmetic. Okay, if you understand the definition, we're just using limits in arithmetic. Okay. Does that make sense? Turn to somebody nearby and talk with them and see if you if you're confused or if you can come up with a question. Because I don't want to just be up here talking to myself.
So it's just similar to what we did. Yeah, like we're still being sequences of knowledge. Does there have to be conversions? Yes. Convergence, they probably went down the same.
Anybody come up with a question, or anyone come up with a question, or it seems kind of clear? Is it all right? Mr. Al.
We have a question.
Yes.
I guess in the limit, the limit of the partial sum converges to L. So the definition of limit applies. What we have a difficulty understanding seems like since we can get as close to L as we wish, why can't we say that therefore the sum is L?
I mean, we say that, but what we mean by that is that the limit of the partial sums is L.
Okay.
Yeah. We don't in normal language, we don't have a meaning for adding an infinite number of terms, right? What does it mean to add an infinite number of terms? Are you allowed to skip terms? Are you allowed to add them in any order? Are you allowed to rearrange them? It turns out that if you're allowed to rearrange them, then you run into trouble. Okay, so you'd like to say the sum of all these numbers is L. Okay, but the trouble is that that's not precise enough. That's not precise enough. It opens the door to possible craziness.
Ambiguity.
Yeah, ambiguity, like the 1 equals 2 business. Okay, so so we have to say what we mean by this is that the sequence of partial sums converges to L. Yeah, and so I mean, this is this confused mathematicians for many years until they figured out a way to do it that didn't result in craziness. Yes, Hannah.
So what caused the very first example of the R equal to 1 plus 1/2 plus n equals to thing equals something that's not true?
That is true. That is true. I mean, in the sense that its sequence of partial sums converged to 2 or to 1, whichever. That was fine. The thing that wasn't fine was what we did on the right before we started all this stuff, where we had that 1 minus a half plus a third.
Why was that a problem?
Well, because we did cancellation. We said we're going to take this guy and cancel this guy. That cancellation basically is saying that we're doing we're rearranging terms. We're not taking them in the right order. We're taking this term and then we're skipping ahead to another term and adding that one. We're skipping back to this guy. We're going to another term. We're taking the terms out of order. It turns out that's actually kind of dangerous, very dangerous. That you can in fact end up with any number you feel like if you do that, if you allow that. You could make your sum end up 10, 3,000, whatever. All numbers would be equal in that sense, in that case. Okay. Well, okay, maybe I went too far into this. But the advantage of this is, so this has some advantage, right? Namely that you can, now that you have this theorem, you can use it, our summation of, the summation of 2/3 to the k being 3, we can now multiply it, right? We also had summation of 1/2 to the k equal 2. Right? Now we don't have to do any more work. We can say, look, by the theorem, you can add these things together, right? 2/3 to the k plus 1/2 to the k actually does equal 5, right? That's okay. We can do this because the theorem says as long as these individual series converge, then the series the sum of their series, the series of the sum will be equal to the sum of the series. Okay. Or you could multiply, this thing, by, if we multiply this thing by 1/3, right, you'd see you get 1, right? That's okay because you can, right? It's basically saying that you can pull a constant out, right? So, right, if I have this 1/3, 2/3 to the k, I can pull the constant out and say, well, this is going to be 1/3 of 3, in other words, 1, right? Because we worked out that this was 3 using the geometric series formula, right? Similarly, right, that if I have this sum of series, right, then I can separate them into individual series, right? And just get 2 plus 3. 3 plus 2, 5. Okay, so that's what this theorem gives you, right? That Now you can do this sort of thing just like you did with in elementary school with just finite sums. Okay, so that's useful. Okay, is everybody okay? Is everyone all right? Okay, so a lot of what we're going to do starting from now is what's called convergence tests. So a way of looking at a series and saying, oh, this actually converges to a limit, or this doesn't converge to a limit. Okay, so that's something that we're going to need. We want to be able to say, so for example, if I have 1 plus a half plus a third, if I have 1 plus a half plus a third plus a fourth plus blah, blah, blah. In other words, if I have summation 1 over n, does that converge to something? Does that have a limit? What do people think? You're adding numbers, the numbers are getting smaller. Does that have a limit? It's very hard to tell, right? Or if I say 1 over n to the 1.1, okay, or make it more easy to think about, 1 over n squared. Does that have a limit? Are you taking 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, blah, blah, blah. Does that have a limit? Right? These guys are getting smaller faster, right? You see they're getting smaller faster. In fact, this one, the upper one doesn't have a limit, becomes infinite, and the lower one does have a limit. It's like pi squared over 6 or something like that. Yeah. So we want to be able to tell, we want to be able to have some tests so that somebody gives you a sequence, gives you a series, and you say, okay, by such and such a test, I can see that this thing's going to have a limit or won't have a limit. Okay. Okay. So yeah, these are called convergence tests, and this is all we're going to be concerned with for quite some time, I should say, like at least a week or 2 weeks maybe. Okay. So the first one is called the divergence test. Okay, and it goes like this. If your series converges, in other words, has a limit, then the terms must converge to 0. The terms must become small. The terms have to go to 0. Okay. And the usual mistake that people make is to think to take this in the wrong order. People will say, if the terms go to 0, then it converges. That's false. Okay, right? This guy's terms go to 0, but it doesn't converge. Right? This guy's terms go to 0, and it does converge. The terms going to 0 doesn't tell you anything about if it converges or if it doesn't converge. Right? Right? But if it converges, the terms have to go to 0. Okay, so does not say if the terms go to 0, then the sum converges. Okay. It does say if the terms don't go to 0, then the series diverges. Okay. Does that make sense? Right? This is what it does say, right? the theorem says if your series converges, oh, hold on, people are still writing. The theorem says if these guys converge, then the terms must go to 0. Okay. Those of you who know logic know that any statement like this is equivalent to what's called the contrapositive statement. That the negation of B implies the negation of A. Okay. In other words, if these guys don't go to 0, then this thing diverges. Okay. Right. So this is the contrapos does say as a contrapositive, right? That if the thing doesn't converge to 0, then the sum must diverge. Okay, so this is statement and contrapositive. Okay, so let me give you an example. If I have the sequence k plus 1 to the k, sum from k equals 1 to infinity, and somebody says, what do you know about this? What do you know about the sequence? Well, you'd say, well, look, so does it converge? Does it diverge? Right? And you'd say, well, the limit of the terms, if I look at the terms as k goes to infinity, maybe you remember what this is. You've seen this before. Tanima, what is it?
I'm sorry, E.
It's E. Right? You don't have to apologize. You knew the answer. Okay, it's E. Right? We saw this earlier. The limit of the terms goes to E, and so we know this thing diverges. Right? Right? If it converge, these things should go to 0, but they don't go to 0, they go to E, so it diverges. Right? So by the divergence test, it diverges. Another name for the divergence test is the nth term test. Nth term test. But I think divergence test is better because then you remember that it only tells you if you diverge. Right? It doesn't tell you about convergence. It's a test for divergence. It doesn't tell you anything about convergence. Okay, if I gave you something like this, k over k plus 1 to the k, as k goes from 1 to infinity, what would you say about that? Jake?
Well, I'm just trying to simplify the stuff in parentheses. So would that just be 1 plus k?
No.
No.
Nope.
Okay. Sorry, I'm kind of confused.
That's okay. That's all right. Right, you've got this k over k plus 1. Earlier we had k plus 1 over k. Now we've got k over k plus 1. K plus 1 over k, that's easy to break up. K over k plus 1, I don't know, not so straightforward. Right? But this is k plus 1 over k to the negative 1. Right? So this is the same thing as k over k plus 1 to the negative k. Does anybody see what will happen to this? To the nth term as n goes to infinity? Are you in there?
Does it approach 0?
No. Tanima? No. Yeah. 1 over e. Yeah, these guys will go to. This is the limit of k going from going to infinity of 1 over, right, k plus 1 over k to the k, right, which is going to be 1 over e. So, again, diverges. Okay, so this is the first test that we give you. We're going to have a bunch more tests, a lot more tests. Let me just quickly try to show you why it works. So here's the theorem. If summation is a k convergence, right, then the a's of k's must go to 0. Okay. So here's the proof. Let S of n be the sequence of partial sums. Okay, let S of n be, as usual, the sequence of partial sums. Okay. So we know that the S of n converge to L. Let T sub n be S of n minus 1. Okay. So it's like a delayed sequence of partial sums. Okay. So it's going to be the sum of the a sub k's from k equals 1 to n minus 1. Okay. Well, T sub n T sub n is also going to go to L, right? Because it's just, it's just one second delayed. And as you go to infinity, it's going to go to the same number. Okay. But then S sub n minus T sub n is going to go to what? If I take the difference of these two sequences, well, by limits and arithmetic, this is going to go to the limit of n as n goes to infinity of these guys is going to be 0, right? L minus L. The limit of this guy minus the limit of that guy, which is 0. But S sub n minus T sub n is I'll give 1 point to the person who's still awake enough to see what the answer is. Jake?
Is it 1?
It's not 1? It's not L?
Minus 1.
It's not minus 1?
0.
0? Are you guys just throwing out numbers? Pi, E, infinity?
A of 1?
What?
Is it A of 1?
Ah, you're so close.
A1? Oh.
Nope.
A something?
Hannah? A-N.
Oh.
It's A-N. A-N, right? Because S sub n is the sum of the guys from 1 to n. T sub n is the sum of the guys from 1 to n minus 1. So these guys minus that guy, right, will be the only one who survives is the last one, A sub n. Right? Right? So what are we saying? That the limit of the A sub n is 0. Right? Right? S sub n minus T sub n is A sub n. Right? The limit of the A sub n is L minus L, namely 0. Okay, I'm sorry I've kept you over a couple minutes. That's it for today.